Ever stop to think about the secret world of physics happening all around you? I mean, every time you stretch a rubber band or bend a paperclip or even just look at a bridge, there are these incredible forces at work. Well, today we're going to pull back the curtain on the physics that explains why things snap, bend, and sometimes break.
I mean, think about it. It seems like such a simple question, right? A rubber band snaps back, a paperclip stays bent. They're both getting stretched out of shape, but their reactions are polar opposites. So what's really going on here? What's the secret sauce that makes them so different?
All right, the answer to that big question, it all comes down to one single super important property: elasticity. Yep, that's it. It's the one thing that separates the stuff that bounces back from the stuff that just stays bent.
So, what is elasticity, really? The easiest way to think about it is like a material's memory. Seriously, it's this built-in desire to get back to its original shape after you've stretched it or squished it. A rubber band? It's got an amazing memory. That paperclip? Well, its memory's kind of terrible.
Okay, to really get this, we've got to learn to speak the language of physics. It's all about cause and effect, push and pull. And it really boils down to two key players, two big ideas we need to get our heads around. So let me introduce you to the stars of our show: stress and strain. They're a classic duo. Stress is the action. It's the force you're putting on something, the pressure you're applying. And strain? That's the reaction. It's how much the thing actually deforms or stretches because of that stress. You literally can't have one without the other. Stress is the cause, strain is the effect. Simple as that.
And for a while, the relationship is super predictable and, honestly, kind of beautiful. It's all thanks to a guy named Robert Hooke, and his rule is called Hooke's Law. All it really says is that the more you pull, the more something stretches. It's a perfect one-to-one relationship. You double the stress, you get double the strain. It's elegant, it's simple, and for most materials, this is how their story begins.
But what happens if you just keep pulling? Well, that perfect relationship, it doesn't last forever. Things get complicated. So now we're going to follow the entire life story of a material as we stretch it, from its happy, predictable youth all the way to its dramatic end. Okay, check this out. This is a stress-strain graph. And honestly, the best way to think of this is like a biography of a material. That line tells its entire life story. As we move along the graph, we're applying more and more stress, pulling harder and harder, and that line shows us exactly how the material is holding up. So the story starts in this happy place called the elastic zone. All the way up to point A, the proportional limit, everything is perfect. The material is following Hooke's law to the letter. It stretches, it snaps back, no problem. Now, if we push it just a little bit further to point B, the elastic limit, it'll still snap back to its original shape. But that perfect, predictable relationship is over. This is it. This is the absolute last chance for the material to go back home completely unchanged. Because the second you go past that elastic limit, everything changes. We've crossed a line. Now we're in what's called plastic deformation. The material is now permanently damaged, permanently stretched, just like our paperclip. If we keep pulling, the stress keeps building until we hit point D, the breaking stress. This is the absolute peak, the most stress it can possibly handle before it starts to physically fail. You can literally see it thinning out. And from there, it's a short, tragic trip to point E, the breaking point. The material gives up, it weakens, and it fractures. The end. Now here's the cool part. Not every material has the same biography. Some have these long, dramatic stories where they stretch and stretch, giving you tons of warning before they finally fail. And others? They have very, very short stories. They just snap. And looking at their stress-strain graph tells you exactly what kind of character they have. Just look at these two totally different life stories. On the left, you've got what's called a ductile material, think copper or steel. See that huge, long section after it gets permanently bent? That's it giving you a warning. It's bending, it's stretching, it's basically screaming, hey, I'm about to fail. But then you look at the right. That's a brittle material, like glass or a ceramic plate. It barely has a plastic phase at all. It's fine, it's fine, it's fine, and then, boom, it's gone. Snaps suddenly, with absolutely no warning. Okay, so graphs and stories are cool, but why does any of this actually matter? Well, it's because understanding this journey, this entire story from elasticity to failure, is, and I am not exaggerating, the reason we can build our entire modern world. Think about it. When a skyscraper sways in the wind without snapping, that's because engineers understood its elastic limit. You want it to bend a little. When the frame of a car crumples in an accident, that's not a failure, that's designed plastic deformation. It's absorbing the impact to keep you safe. From aircraft wings that need to flex, to phone screens that resist shattering, to even medical implants inside the human body, every single one was chosen because an engineer read its life story, its stress-strain curve, and knew it was the right character for the job.
You know, it all boils down to the same thing. Doesn't matter if you're making a simple slingshot or a 1,000-foot-tall skyscraper, you have to know its limits. You have to know where it bends, where it breaks for good, and where it shatters completely. Knowing that breaking point, it's everything.
So, I'll leave you with this. The next time you grab a rubber band, just before you flick it, take a second. Think about its story. As you stretch it, are you just in that happy, elastic region? Are you pushing it to the brink, right to its elastic limit? Or are you about to write its final chapter? You're not just playing around. You're a physicist, testing the limits of its story.